Okay. Okay. So, okay. Your choice where to start.
We start with 12.
Okay, let's start with problem 12. Oh, what is happening here? Okay.
What problem do you think would be most useful or important?
Well, they're pretty much the same. This chapter, at least the problems that I have selected are not that difficult. And I think that you're going to discover that once you start. Okay, so problem 12. Problem 12. Look, what we have is the definition for pressure, force for unit area, definition of mass density rho as mass per unit volume, hydrostatic equation, P2 is P1 plus rho GH, and the Bernoulli's equation, P1 plus rho G Y1 plus 1/2 rho P1 squared is equal to P2 plus rho GY2 plus 1/2 rho P2 squared. So here you just need the definition for pressure. So in this problem, you have here is the well, and when it is in contact with the ground, it looks like this. So of course you have here the rest of the tire looks like this, and the area that is in contact with the ground is not a single point as it would be if you had ideally solid, rigid circle, but you have some area that is in contact. And since the pressure inside the tire is acting on the walls in downward direction, the ground is acting in upward direction with the force that is going to cancel the force that is going to cancel. The force has to cancel the weight of the person and the weight of the bicycle. In other words, so this force for my version, this force is going to be the sum of the weight of the person and the mountain bike. In other words, it is 735 plus 98. So it is 833. 833 is the weight in newtons. Yeah, and the rest is easy. You just say that the force, also should be a result of the pressure multiplied by area. They give you the pressure. So you have pressure times area is equal to 833. And therefore the area is equal to 833 divided by the pressure that they give you. And after that, you have to divide this number to 2 because most bicycles have 2 wheels.
Nobody asked a question about this. We'll go over 13 as well.
Okay, let's see if anybody is going to ask anything. So the units are all adjusted so you to get the answer in square meters. There shouldn't be a problem. Just make sure that you enter the numbers that they give you. Okay, which one?
13.
Okay, a scuba diver descends, internal pressure remains at atmospheric pressure, while external pressure is increasing. The difference between external and internal pressures can rupture the eardrum, and they rupture when the pressure difference is 35 kilopascals. What is the depth where this would occur? Well, there is no any trick here except, well, all the units are fine, so everything should work. They should give you the density of seawater. Oh, they give it. Okay. So, well, here it is. The pressure inside his ear is atmospheric pressure. The pressure outside is going to be, well, it is going to be atmospheric plus rho GH. So pressure inside his body is 1 atmosphere, let's say. Pressure of outside of water is going to be atmospheric plus rho GH. So why is it? Because here is the water. So the water, when you're here, you're going to be subject both to atmospheric and this hydrostatic pressure due to this H. So the surface of water is under atmospheric pressure, right? And that's it. So the pressure difference between out and in, P out minus P in, it's going to be rho GH, and it shouldn't exceed, it should be at most what the number that they give you. 35 times 10 to the third for my version, 10 to the third pascals. So they give you rho, that you know the value of G, the depth H is going to be 35 times 10 to the third pascals divided by G and divided by the density that they give. This should give the answer. see remarks here. So again, from this chapter, there are problems related with static fluids like this one, and there are problems related with fluids in motion, for which you have to pay. There are only 2 or 3 types of those problems related with motion, fluids in motion. So you have, once you do from each type 1 problem, you're going to feel comfortable with.
I might just be putting it in wrong or something, but the solution for number 12 didn't work for me.
Well, let's see. This is approximately, so just looking at the numbers, this is approximately 3.5. Maybe 3 point, yeah, approximately 3.5. Let me try 2.5 for my version. Oh, I entered it in the wrong place, I think. I didn't enter it at the right place. I was supposed to enter it here. 3.5 approximately. Well, you need a little bit better accuracy, but better accuracy needs a calculator. And you see that this, even this approximate solution works for me.
No,
So-
no, the other one.
Oh, the previous one.
Yeah.
So what did we get about, what was the answer that we got for the previous one? It was,
It was like, I got 9.42 e to the negative
so
4.
it is, for me, it was 833 divided by 6.65 times 10 to the 5th. And divided by 2 also, divided also by 2.
Oh, okay.
Right? We said divide to 2. So for me, this is the answer, and you can calculate and it should work, but yeah, okay. Let's see. Other remarks? Okay, what's next question?
Maybe 17.
Okay. Airplane with wing, surface area, lift force. Level of flight means that the lift force and the weight are exactly cancelled. They give you the airspeed above and below. What is the weight? So this is one type of problems related with fluids in motion. So here is the wing of the plane, and this airspeed here is larger, call it V1. And for me, V1 is 66.9 meters per second. And the airspeed is V2 down. For me, it is 57. They give you the surface area of the wing, of the wings. What is the weight? Well, the weight, they want the weight in newtons. So you have the weight is this way, and it is exactly canceled by the lift force, because they say that the plane is in level flight. The lift force in magnitude is equal to the weight, and it is going to be equal to the area of the wing times the pressure difference between the pressure at point 1 and pressure at point 2. So it is P1 here, P2 here. So the pressure difference is going to be P2 minus P1. Pressure difference. And now look, the wing of a plane is not very, it is very thin. So the height on top and the bottom is approximately the same. The y1 and y2 are approximately the same. So you can cancel them. And you're going to get move, let's say, this pressure to the other side of the equation with opposite sign, move this speed to the other side of the equation with opposite sign. And you're going to get that pressure P2 minus pressure P1 is equal to 1/2 density factorial V1 squared minus V2 squared. And that's it. So this is the pressure difference. Once you cancel those two terms and once you rearrange and factor out. So your answer should be the area that they give you times 1/2 times the density of air times the speed on top V1 squared minus the speed on bottom squared. So this should be the answer.
If this was on an exam with the density of air that we were.
Yeah, the density of air has to be given, yes. And
So since on this one, like I just Googled it and it worked.
yes,
I was wondering. If I
yes.
could use-
Well, the number has to be given, of course, always. The number has to always be given, and yeah, that's it. The density of air is something that you need.
Can you use that 15?
Any questions here? Okay, one way to administer an equation is using, well, a gun is a bad word for a medical device, but okay. So you want to spray this vaccine with sufficient speed to pass directly into the tissue beneath the skin. The speed has to be high because the vaccine is high pressure. So you need high pressure to spray this vaccine with sufficient speed. They give you the density of this vaccine. Okay, it's very dense, but whatever. The pressure on the surface of the gun is this number above. The pressure on the surface, oh, I see, is certain number above atmospheric pressure, small dosage, reservoir stationary, and okay, so this is what you have. So maybe some reservoir with the vaccine in it, and you spray it to certain opening like this. you have the density, so the vaccine is right here. Yes. The pressure on the surface of the vaccine. Well, here is the pressure T1, or let's make it T1. Pressure here inside. And it is gauge pressure. As the vaccine is exiting here, its pressure is atmospheric pressure because it is, but it is moving very fast. So that here, the pressure P2 is 1 atmosphere, and here, the speed is some speed V2.
So is P1 the given pressure
Yes,
times 1 atmosphere?
yeah, plus 1 atmosphere, yeah, plus 1 atmosphere. So, but after that, it is going to cancel out. So you don't need to add or subtract. You're going to see that. Well, what is the speed of this vaccine while it is in this reservoir? The speed is V1 approximately equal to 0 because you assumed it is large reservoir. And when you spray a little bit, it practically doesn't move much there. So also the height of point 1 and point 2 are the same. So look what you have. This is canceling this. This is 0. And therefore, you're going to have that P1 minus P2 is going to be 1/2 rho V2 squared, where V2 is what you want to figure out. This difference of pressures is exactly the pressure that they give you. For me, it is 4.9 times 10 to the 6th. The density is given, solve for the speed, and you're going to get it. Right? So you have the speed V2 is square root of 2 times the number that they give you, the pressure difference, divided by the density, everything under square root. This should work. Work here. So this is another example of Bernoulli's equation application. It's not much different from the previous one, but still you need to realize what are the numbers that they give you and where they live. You see how short those problems are. Once you figure it out, it is almost like multiple choice question. You still need a calculator to take square roots, but not much more.
Yeah, would you just like show the terms, how they cancel out to get that final equation?
Well, this term is equal to this term because they are of the same height, approximately. The speed of the vaccine inside the reservoir is almost 0 because the reservoir is something large. And if you spray a little bit, this vaccine is almost not going to move. So this is 0. And You just move P2 to the other side. P2 is the atmospheric pressure. And that's it. So you're going to get, once you take those things into account, you get P1 minus P2 is 1/2 rho V2 squared. That's it. This is 0, this canceled. That's it. So the only thing that you did practically after canceling and taking into account what is 0, the only thing that you did is move P2, the atmospheric pressure, to the other side of the equation with opposite algebraic sign. This is what I wrote. Other? Okay. Other problems?
Can you do 16?
Okay, so again, Bernoulli's equation, but this is a problem related with biology, so we have to understand how it works. So you have normal segment of artery and narrow segment of artery. Here is the artery, and suddenly it becomes narrow. Now, maybe after that it may. But here the cross-sectional area is A1, the speed of blood is V1, the pressure of blood is P1. While here at the narrow segment, the speed is V2, the cross-sectional area is A2, and the pressure is P2. So you're going to discover, of course, that the pressure in the narrow segment, surprisingly, the pressure there is lower. So first, in this problem, you have to use the equation of continuity, which I forgot to write, which is equation about the hose that gets narrower. The equation of continuity looks like this. Area, cross-sectional area of the hose times the speed of that spot has to be the same as the other cross-sectional area times the other speed. So this equation solved for the speed V2 in the narrow segment is going to tell you that it is area ratio of areas times V1. For my version, the ratio of areas is 8:1, right? So this ratio is 8:1. So this is 8 times V1, 8:1. The normal segment is 8 times wider in cross-sectional area. So now you have the speed V1 and V2 in the two segments. And again, now look at, if you look at Bernoulli's equation, the height of the narrow and the normal segment is the same. It's a horizontal artery, yes.
So if those are the same, then PGY is just gonna cancel out, like if they're the same height.
Yes, PGY cancels out. Yes, this go away. Yeah. And you're left with the other four terms. They're asking you about the pressure difference. And when you move P2 to the other side of the equation with opposite sign, and this term to the other side of the equation with opposite sign, you get P1 minus P2 is equal to 1/2 rho V2 squared minus 1/2 rho V1 squared, which of course can be written in a short way as 1/2 rho times the difference of the squares. That's it. So this is the answer. Pressure difference between the two sides.
So again, we would just Google the density.
Oh, the blood density, yeah, should be given. Here they say table 111.1 for appropriate constants. So you can click on this link and you're going to get the mass density of blood. Notice the result is going to be a positive number. This means that the pressure of the white spot is higher than the pressure of the narrow spot. It's exactly the opposite of what your intuition says. Okay. Questions? Yes.
So then, since it's 1/8 of the original, how come we multiplied it by 8?
So,
Wouldn't it be decreasing?
so the large is 8, the small is 1.
Okay.
So if A1 is 8 units, this A2 is 1 unit. So the ratio of 8 to 1 is 8.
Okay.
Any other questions? Any other problems? Which one?
PP.
So rectangular roof. But flat, not rectangular roof. So here is flat rectangular roof. It tells you we're given area, right? They give the dimensions, so you know the area of the roof. And they give you the maximum force that this roof can survive. They give you the density of air. Here it is. You don't need even to Google it. In this problem, they give the density of air. Find this, what's wind speed will this roof blow out. So here it is, some air speed right here. The wind is blowing with speed V1 right here that you want to figure out. The pressure outside the roof is pressure P1. The pressure inside the roof is P2. The speed of air inside the roof is V2 equal to 0, right? Inside you don't have much motion of air. And the difference between inside and outside, as far as height is concerned, is almost nil. Y1 and Y2 are practically the same if the roof is normal thickness. So those two terms are practically the same, they cancel out. And you get for the pressure difference, and notice that the higher pressure is inside. So I can write the pressure difference as P2 minus P1. So in other words, I'm moving P1 to this side of the equation in order to get positive number and you to understand what's going on. So you have Okay, you have V2, the pressure, the speed of air inside is 0 also. So you're going to get this P2 minus P1, pressure difference between in and out, is going to be equal to equal to 1/2 rho V1 squared. And that's it. So the force is area multiplied by this pressure difference. V1. And that's it. So this is area multiplied by 1/2 rho V1 squared. They give you the force, you have to solve for the speed of air. So you have V1 squared, let's say, is equal to 2 times the force that they give you, divided by the area and divided by density of air. And therefore, the speed that you're looking for is square root of 2 times the force that they give you divided by the area of the roof, and also divided by the density of air.
So the P2 minus P1 is just equal to the force given.
It is pressure difference. To make it a force, you have to multiply it by the area. So pressure difference multiplied by the area is going to give you the force. The net force due to the motion of air. It's practically like the lift force. And again, notice that the pressure inside the house is higher. So the roof is just going to go upward. Other?
MCAT question.
Mhm.
A 30-kilogram girl sits on a seesaw at a distance of 2 meters from the
Yeah, it
fulcrum.
would be good if we project it so people to
Sounds
see it, but how to project it? Why don't you, if you have it as a, what kind of file is that? Or it is it's a huge from a book or what?
No, it's just from. Yeah, it's from Kaplan.
Do you have a port that we can connect here? This port?
Oh, that's okay.
Let me see, this type of port, this type. Not here, I don't see it here. See it
No,
here, what on the back?
no.
Can you mark it? So just mark the problem. Do,
Can I email it to you?
yes, and try to project it. So we're done with the homework, right? And you see how easy it is once you understand what is going on there. Yeah.
I just have a quick question. So for number 14, would it be similar to what we did for 16?
So yes, what was 16? It is pretty much the same as one of the other problems that we solved.
And it's still got the ratio.
No. Here, this problem is just like problem. Okay, let's 12. Which one was that? 14?
Yeah.
Okay, let's do problem 14 while I'm waiting for this email. So you want the pressure difference to be 1/10, and you only need to use the equation for static fluid. You don't need to use the full Bernoulli's equation. So here it is. Here is the water, and you're at this depth. This is approximation because as the person goes in, his body is squeezed and the pressure inside his body increases. But we're going to neglect that increased pressure. And we're just going to assume that the pressure inside the body is exactly equal to the atmospheric pressure. So this means that if you look at point one is here at the surface of water, and point two is somewhere deep where the pressure reaches some height, some depth h where the pressure increases. So the pressure difference between point one and point two is P2 minus P1 is rho GH. So they say the pressure difference is 1/20th of an atmosphere. So this is 1/20th of atmosphere. Should be rho GH. So you have to convert atmosphere into pascals. And I believe that one atmosphere is
1.013
Yeah.
times 10 to the fifth.
So you have 1/20th of 1.013 times 10 to the fifth pascals is rho GH. And therefore the height that we are talking about, the depth H that we're talking about is 1/20th times 1.013 times 10 to the fifth divided by the density of water and the acceleration due to gravity. They give you the density of water again. It's different number this time than the number in the other problem. So in this problem, you don't have fluid in motion. So the hydrostatic equation is going to be sufficient. Okay.
I actually figured out the MCAT question. I mean, you still go over it. It's something we've done before.
Okay, let's see. Okay, finally an MCAT question, which I don't know if you see it, but okay, so you should be able to read it. You have a 30-kilogram person sitting on a seesaw at a distance 2 meters from the fulcrum. Where must her father sit to balance the seesaw? If his mass is 90 kilograms. So it is a matter of torque, and don't count on the real MCAT to get questions like this, because this one is simple. And so it looks like this. So here is the girl, and her weight is so mass 30 kilograms. So it is M1G, M1 is 30. 2 meters. So here is the fulcrum. And this distance is 2 meters. Call that distance L1. 2 meters. And here is the father on the other end with a mass of M2 times G, where M2 is 90. He is at a distance L2 from the fulcrum. And well, what is this distance? L2. That's what I want to figure out. And you say, well, clearly, just use the torques. The net torque has to be 0, so the seesaw not to rotate in any direction. So the torque generated by the girl's weight is going to be M1G times L1. It is in positive direction. The torque generated by the father is going to be M2G times L2. And you cancel the acceleration due to gravity, and you find that the distance L2 is equal to M1 divided by M2 times L1. In other words, it is L1 divided by 3, because M1 is 30, M2 is 90, so the ratio is 1/3. So it is 2 meters divided by 3. 2 meters divided by 3 meters. 2/3 meters, which is 0.66 meters distance from the fulcrum. Well, again, usually MCAT questions are much more either tricky, or they give you to read some long passage, and after that they ask about some small detail from that small package, but that detail may require still arithmetic. Okay.
Do you have time to go over one with Ohm's law?
Ohm's law, yes, if you email it, we probably have exactly this amount of time. So another MCAT question. Okay.
Hopefully that shows up. Okay.
So I have to leave in about 2-3 minutes, but
If not, I can just say it next time.
let's see.
It feels so small.
Oh, I can,
You can click on the image. And I think they're.
okay, perfect.
they're
Oh,
good.
it is an image, okay. It still has to be a little bit magnified. Oh. I don't know.
Sorry,
No, that's
I'll find a better
perfect.
way to do this.
So membranes are often taught as wires of A, proteins, glycoproteins, and lipids. Tracts are equivalent to resistors that decrease the current to the membrane. Okay, yeah. Research are interested in modeling electrical conduction in cells using two circuit systems. Circuit system A, I guess. So I guess that the first one is A, is it? Researcher set up two resistors in series, so this should be A. This is, wait a second. Yeah, this is A. Notice that even though they look parallel, they're connected in series.
Mhm.
Set up a circuit, two resistors in series to replicate the position of two adjacent proteins within the cell membrane. And B, the researcher set up circuit with two resistors in parallel to the model. Okay. Okay, so what is the question? Is there
Oh,
a
the
second
question, yeah,
page?
there's a second picture of the question. It's just like the first question. Maybe from there.
Oh, okay, so it is down there. Which of the following formulas best describe the equivalent resistance of system A? So system A was in series,
Mhm.
and the equivalent resistance is given by this, by the sum of the two resistances.
Okay. So if it had been broken up like system B,
For system B, this is the equivalent resistance. In system B, the two resistors are in parallel, right?
right?
So this is, so yep. They're in, well, for system B, let's say, are they in parallel or not? Oh, system B, it is a little bit more complicated. Let's see. Oh, it is very good connection.
So,
Well, the system B is going to have equivalent resistance equal to only this. This
okay.
is not relevant at all.
Oh, really?
Yeah. So just look, you're connecting this way. Nothing is going to. Oh, yeah, wait a second. Well, it is, we have to use Kirchhoff rules to figure out the
Okay.
equivalent
Well, we can
resistance.
do it next time.
And yeah, we have to do it next time.
Okay.
Let me see if there is a way to think about it.
So the next question says, which of the following variables remains constant across the entire system B? The current voltage, power, or capacitance? Would it be the power?
So those two resistors are neither in series nor in parallel. Okay, so let's remind me next time. Remind me next time to go over this,
Okay.
and I just have to end it right here.
Let's see if I can find a better way to.
Well,
Take a
that's
screenshot.
you don't need to bother. It is going to be enough for us. Okay, so we're finishing.
Thank
we're
you.
finishing, of course. Let's see. Finishing here.